Another important kind of AI is pathfinding. That is, given some starting point and some goal, how do you get from here to there? There's lots of examples of this in two-dimensional space. Suppose that you are trying to manage the Mars rover and you wanted to drive from here to a point over there and you wanted to choose a path on its own while avoiding rocks. Well, you have a starting point, you have an ending point, you have a bunch of obstacles, and you want it to figure out what's the best way to get from here to there. The same kind of thing happens if you are the UPS delivery company and you want to get your trucks to go from here to there, given red lights and traffic and what streets are available. And it gets a lot more complicated if you want to have multiple stops, that if you don't have just one goal, but maybe you have 10 goals, and you want to figure out not only how do you get from each one, but what order should you go in. That's a really hard problem. It's called the traveling salesman problem. And of course, again, there are games. You might be playing a game, a computer game, and you're flying some ship in space, and there are some, computer ships, AI ships, and they are driving around on their own, right? The program that's driving those computer ships has to do with the pathfinding problem. The reason that pathfinding is hard is because a lot of times there are obstacles that get in the way. So if you simply try and go straight from the start to your goal, what can happen is you get stuck, right? You can have these kind of greedy algorithms where at every point on the way you just say, well, that's where I want to get to, let me just go in that direction. If you do that, you get blocked, and if you don't have any special way of backing up and looking around, well, then you're stuck and you can't get to your goal. If you do have a way to back up and look around, then maybe there's a alternative way of doing it, right? Which is going forward, realizing that you're blocked, and then start looking around and going around until you get to the goal. This has the nice characteristic that at least it succeeds, but it's inefficient from the perspective of the path itself that is discovered. What we'd really like is to discover a path that somehow doesn't waste our time going down to that blocked area. This succeeds, and it's efficient for the resulting path. Okay? There's another kind of efficiency, which is how efficient is the algorithm at discovering the efficient path. But let's not even worry about that yet. The first thing I'd like to do is just to discover any path at all. So how do we do that? So let's dive into this path search algorithm. In the simple case where we have a two-dimensional grid, and we want to go from one place to another place, and there might be some obstacles in the way. Maybe there's some cells in the grid that we're not allowed to walk through. How do we get from one to another? Well, think about it. You as a person, if I were to give you this problem, how would you solve it? Well, if you start at your start node, and you know you want to go over here, you probably want to start moving in the direction of your goal node, right? And we can use our indexes to figure out, what the direction is, right? We have our row and column numbers so we can move in that direction. Maybe what we want to do is start walking in that direction, and if we don't run into an obstacle, we just get to our goal and we're done. So that's easy enough. That's not the hard part. But suppose we do run into an obstacle, then what happens? Well, then I guess we kind of have to start backing up and exploring, right? So that means we have to have the ability to not always go directly in the direction of what we want, but to be able to go in other directions too. So we might want to have the sort of concept of knowing what our neighbors are, so we can go in the direction of our neighbors. But when we back up, we wouldn't want to back up exactly where we came from, because we already were there. So we have to make sure that when we're exploring, we only explore places we haven't been, right? So we have to have this concept of a list of visited paths, so we never waste our time visiting paths we've already visited before. And we can only be exploring one place at a time. So at each step along the way, we want to be able to say, well, from here, I want to go forward if I can, but I want to put on a list of possible places to explore my side neighbors. Then if it doesn't pan out, we can go back to a list of places that we'd like to explore and explore those as long as those aren't places we already have explored. Yeah, that is actually the essence of exploring, right? We have a current path we're exploring. We generate a list of places we've already explored so we don't revisit those. And we keep a list of places that we'd like to explore if the current approach doesn't pan out. Let's draw a sketch to see if we can make some sense of that basic approach with a little bit more detail.
So let's look at what the general graph search algorithm looks like on a specific example. We're going to draw a straightforward example, which is a 4x4 grid. And I'm going to put into the grid a start point, which is over here, and a goal, which is over here. And to make this a little bit easier to understand, I'm going to give each cell a label, starting at 1. And finally, to make it just a little bit more interesting, I'm going to block out one of the cells as being illegal to visit. So finally, what we're going to do is have a list of our data structures. Over here, we'll keep our list of paths that we've already visited, so we make sure we don't revisit those. And over here, we'll put our frontier, which is the list of paths that we have not yet visited, but we need to. Okay, let's start the algorithm. The basic idea, as we've said, is to have a current path that we check to see if we're done. If we're not, we add on to the path by looking at our neighbors and take those new paths, put them on the frontier. And then we take paths off the frontier and keep on and process them in the following way. And then we add them to the visited list when we're done to make sure we don't revisit paths that we've already checked. So we initialize the algorithm by putting our starting cell on the frontier. So the way that we're going to write these out is we're going to just have lists of cell names. I'll sometimes call them nodes. And that list will represent the current path. So here's the algorithm. After the initialization, we take the top item off of the frontier and put it on our current list. Maybe we'll say this is our current path that we're processing. So we take 13 off the frontier list and take a look at it. We say, are we done? Well, the way we check we're done was we look at the end of our path, the last node on our path, which in this case is 13, and check to see if it's equal to our goal node, which is 11. 13 is not equal to 11, so we're not done. So then what we'll do is we will look at all of the neighbors of 13, and for each neighbor that results in a valid path, we will add it to the current node, the current path, and add it to the frontier. So the way we're going to do this is to make this algorithm more efficient. We will always pick the neighbor that is in the direction of our goal. If we were to write this algorithm out in code, we wouldn't have to do that. It just makes the search more efficient. But for this example, I will. So we'll go in that direction. From 13 towards 11 would be 14, but 14 is blocked, so we can't add that to our path. Instead, we'll add 9. So the way we do this is we take our current path, 13, and add 9 to that path. And that's the only thing we can add. We can't go left or down because those are not valid. Okay, we're done. We take 13 off of our current list and added it to our visited path. Okay, next round of the algorithm. We take the top item, the top path from the frontier, 13, 9, remove it from the frontier, and add it to our current path. So that's going from here to here. Are we done? No, because 9 is not equal to 11. So we go through all of our neighbors and we'll add them, and if they're not a illegal or already visited path, we'll add it to the frontier. We'll start in the right direction, 13, 9, 10. 13, 9, 10 is not visited, it's not already on the frontier, so we can add it to the frontier. What else can we do? We can't go down because that would be a repeat. That would be adding the node 13 to the current path, so we'd have 13, 9, 13. We don't want to repeat nodes, so we're not going to do that. We can't go off the grid, and the next thing is 5. 1395, it's not visited, it's not on the frontier, it's not illegal. Let's go ahead and add it to the frontier. Finally, we can take the current, we're done, so we take the current path out of the current list and added it to our visited list. Okay, next round. Let's take the next item off the frontier, 13, 9, and 10, and see where can we go from here. Well, let's first, are we done? Right, we're now over here. No, 10 is not the goal node. So let's look at our neighbors and add them to our current path, if they're not repeats. Well, let's add in the right direction, which would be 13, 9, 10, 11. It's not visited, it's not a repeat, so we can add that to the frontier list. And where else? We can't go down. That's a bad node. We can't go left. That would be adding a node already on the current path. But we can go up. 13, 9, 10, 6. That's not on the visited list. It's not on the frontier. So we add it. 13, 9, 10, 6. And we're done for now. So we remove the current path from the current list and add it to visited. Okay, repeat. Take the next item, the next path off the frontier list, 13, 9, 5, and add it to current. So now we're visiting this one. Okay, are we done? No, we're not. 5 is not equal to 11. Okay, let's go add our neighbors. The next one might be, say, 13, 9, 5, 6. That's not visited. It's not on the frontier, so we add it to the frontier. 13, 9, 5, 6. Where else can we go? Well, we can't go down because 9's on the current path. We can't go left, that's illegal, but we could go up. So that's not visited, it's not on the frontier, so we'll add that. 13, 9, 5, 1. And we're done. So we remove the current and add it to visited. 13, 9, 5. And we do it again. Take the next item off the frontier list. 13, 9, 5, 11, which takes us here. And we check, are we done? Look at the last node on our list. 11, is it equal to the goal? Yes, it is. Congratulations. So we return this as our current path. And we can happily just indicate that this is the path we found. Our algorithm successfully found a path, avoiding the blocked nodes from the start to the goal.